Okay, we've got some idea how to represent and sketch the electric field at a point. What we want to do is go ahead and do something I alluded to at the end of the last video, which is calculate the field at the 10 meter, 7 meter point. If Q2 is negative 0.003 coulombs and it's located at 17 meters, negative 10 meters. So go ahead and do that calculation, see what you get. Okay, the first thing you would want to do is calculate the electric field at this point due to this charge. Point is 10 meters, 7 meters. This point is 17 meters, negative 10 meters. We could draw the triangle. I'm not going to clutter up the picture, but we're going to have to go negative 7 meters this way, 17 meters this way, which means that we're going to use, we're going to say the electric field, we're going to call that the electric field E2, the contribution of a charge Q2. And we're going to do K times the charge, and I guess we could call that Q2. But I'm not going to. I'm just going to say, okay, Q2 is going to be the charge here. That's going to be your 0.003 coulombs. Now, remember when we do the force, we do K times Q1 times Q2, etc. When we got the electric field, we divided out that second charge. Okay, well, the second charge isn't Q2 here. Here's the second charge. This is the point at which we're calculating the field. We divide it out by this charge, leaving us only this charge that I've called Q2 here. That's going to be the charge here, the 0.003 coulombs. R is going to be the distance from here to here that we get using the Pythagorean theorem. The R vector is going to be your negative 7 meters times I plus your 10 meters, or 17 meters times J. And the entire calculation is very straightforward. So we just plug things in. Our 9 times 10 to the 9th Newton meter squared per coulomb. For Q, we use the 0.003 coulombs. R squared is going to be, well, okay, R squared is going to be the square of this leg of the right triangle plus the square of this leg of the right triangle. That's going to be 7 meters, so the square is going to be 49 meters squared. This is 17 meters, so the square is 289 meters squared. We add those up, we get 338 meters squared. That's our R squared. And our R, of course, our magnitude R is just the square root of that. So there we got 338 meters squared here, with the square root in the denominator, and the R vector is our negative 7 meters times I plus our 17 meters times J. And we do all that, and I think we get something close to 300 newtons per coulomb times I minus 740 newtons per coulomb times J. And the one thing I didn't write down here, I didn't write my negative sign here. Without that, the calculation would come out with the opposite sign. So that our situation is this. We've got our first vector that we calculated long ago, 1,050 newtons per coulomb times I plus 405 newtons per coulomb times J. The second vector, this one here, it turns out to be this, 300 newtons per coulomb times I minus 740 newtons per coulomb times J. So the resultant electric field is, well, the I components are 1050 and 300, adds up to 1350 newtons per coulomb times I. And the J components, 405, negative 740. We'll round that off to negative 340. It's actually negative 335. But negative 340 newtons per coulomb times J. So that adding these two fields gives us this resultant, and now we have the electric field at that point. Now, we did this implicitly without really stating it, that if we have two or more charges, the electric field at a point is the sum of the electric fields from all those other charges. We just add them up. That's a principle of superposition. You'll read about that in your textbook. And of course, if we're trying to find the force at this point, we could have found the force directly using Newton's second law if we knew what the charge was here, or we could calculate the electric field and multiply that by the charge. because in calculating the electric field, we've left out the charge that would go at this point.